So to finish up, there's one last issue that's extremely important, and that is that we want to relate this hydrogen explosion to the energy that each of us consumes each day. That is, we eat breakfast, lunch, and dinner. We combine all those carbon-hydrogen bonds with oxygen, and we generate the heat that's required to sustain our body temperature and the energy required to convert to kinetic energy for walking, running, whatever we're going to do. So let's take this balloon explosion and let's calculate the energy that's been released in that chemical reaction. And we start out with the fact that we need the balloon volume, and that balloon volume that we just blew up is just about 5 liters. But this 5 liters allows us to calculate the number of moles of hydrogen, and that we can calculate by recognizing that a mole of gas at standard temperature and pressure corresponds to 22.4 liters per mole. So if I take my 5 liters and I divide that by 22.4 liters per mole, that turns out to be 0.22 moles of H2. Good. Well, that allows me to calculate the chemical energy release because I know that I have 285 kilojoules per mole of energy released in this hydrogen explosion. So I can simply multiply 0.22 moles of hydrogen times the energy released per mole. That's equal to 285 kilojoules per mole. And when I calculate that out, that gives me 64 kilojoules. And then I can convert that to joules. That's 6.4 times 10 to the 4 joules. That's the energy release from the explosion of hydrogen as it mixes with oxygen. All right. So I have 6.4, 10 to the 4 joules per explosion. Now I have to turn to the question of this energy comparison. And I want to relate that energy release from the explosion to the energy that each of us consumes per day, energy of human per day. Well, I can calculate that pretty quickly because it comes down to comparing how much energy you consume each day. Now, this varies from person to person. We're going to take 2,000 food calories. And now we have to be careful because a food calorie is 1,000 actual calories as it's used in science. So I have 2.0 times 10 to the 3 large calories, and that gives me 2.0 times 10 to the 6 actual calories. But I also know that it's joules that I want to convert this to, and there's 4.18 joules per calorie. All right, well, that allows me immediately to take my 2.0 times 10 to the 6 calories of food consumption per day and multiply it by 4, we can call it 4.2 joules per calorie, and that gives me 8.4 times 10 to the 6 joules consumed per day. Well, now I have exactly what I want because I want to take the ratio of the amount of energy that each of us requires per day and divide that through by the energy release in that hydrogen explosion, which was a pretty impressive explosion. So we can immediately calculate that ratio. That's 8.4 times 10 to the 6 joules per day that each of us consumes. We divide that through by 6.4 times 10 to the 4 joules per explosion, and we come out with the recognition that each day we go through energy equivalent to 130 explosions. That's pretty impressive when you realize it. And then all of a sudden we say, well, I also want to understand the relationship between energy and power. So if I'm consuming 2,000 calories a day, what's my power output? So we can calculate that very easily because we know that the number of seconds in a day is 8.6 times 10 to the 4. So I have 8.4 times 10 to the 6 joules per day, and I divide that through by 8.6 times 10 to the 4 seconds, and that gives me a very interesting number. That's 98 joules per second. Aha, but then I realized that a joule per second is a watt. So that means I have 98 watts. So each of us is essentially equivalent to a 100-watt light bulb. We're sitting there burning carbon-hydrogen bonds in the presence of the oxygen that we breathe, and each of us is then equivalent to the power consumption of a 100-watt light bulb.